I can wait. Herman, hello.
Hey, how's it going?
Good. Welcome. And Patrick, what's up? Similar to the Monday crew we have going on here today. Think there's anyone else stuck in the internets right now? I have no idea why. Oh, it's Afra, hello. Think anyone else is stuck in the internets right now is the question. This is like in those 90s or like early 2000s cartoons and TV shows where people would just like actually go into the internet and they have all these obstacles they have to do. It would personify everything. I feel like that's that. Whenever I open a Zoom call, it takes about like 30 seconds to a minute for everyone to show up. And I have no idea what you guys are doing, but I assume you're struggling to get here in a personified version of the internet. How's everyone's last minute class going?
Good. It's going good.
Nice to know. Hectic. Liam's here. Hello, Liam. What's going on? See, I knew at least one more person was going to show up. Well, we have 5 people today, including me. I have to include me to really buff the numbers up a little bit. But the point is, that's a pretty. Oh, and Safa. What's going on? Hello, Safa.
What's up, Professor?
We're just talking about our last minute class. How's it going for you?
What'd you say?
I said we're just talking about the last minute class over here. How's that going for you?
It's a shame, Professor. It's a damn shame. I'm
What's
gonna
the
miss
damn
this
shame,
class.
Safa?
Huh?
I said, what's the damn shame?
Oh, I'm gonna miss this class.
Aw, thanks, man. Thank you, Safa. That's exactly the kind of ass kissing I expect out of all of you.
Yo.
No, thank you so much, Safa. I'm gonna miss you guys too, for real. It's been a great semester, and I could keep talking about math forever. Like, it's not like legitimately, this is just the beginning of what I hope to be, not just a sequel or a threequel, but like a Marvel Cinematic Universe of math for you all. But anyway, because it's the last day of class, we have a lot to cover. Let's keep the tears for the end. And for now, actually, do what we're here to do, and that's learn some freaking math. So let's do it. Who's excited? Liam, I feel like Liam, that frowny face came in kind of late. I couldn't tell if you were frowning over the fact it's the last day of class or frowning over the fact we're actually starting math. I'm going to assume it's the first one. And we're going to get going here because today we actually have a really fun class because we're actually going to define what the heck a function is. Maybe. Oh, this is fun. Remember this? This hasn't happened in a while. This is back. There we go. Get that pencil later. The point is they're actually going to talk about what a function is beyond like the middle school definition. And it actually is kind of deep and really awesome. So let's start talking about it. First things first, we're talking about functions. And I'm going to go kind of fast today because we have a lot to cover. So please stop me if you guys have any questions. And feel free to email me if you want to go over any of this in more detail because we can talk later. But the point is we're talking about functions. Specifically, we're doing 7.1/7.2, and we're going to dip our toes into 7.4 today. So let's go back over what the middle school definition of a function was. And the middle school definition of function is a function is a thing, right? Like, what's the thing? Like, but anyway, it's a thing that takes in inputs from a domain and spits out outputs in a domain. At the basic level, that's what a function does, and that's what they told you it does in middle school. At least they told me that in middle school. I have no idea what the kids these days are learning, or whatever, Common Core. But anyway, the point is, an example of this would be the function that goes from the interval 0, 5, that doesn't include 0, but does include 5, and spits out things into the real numbers. By the way, I didn't mention this last time. This arrow right here has absolutely nothing to do with like the if P then Q arrow. Arrows are usually like 5 different things in math. One of them is the whole if P then Q, the implication arrow. Another one is the limit arrow, where you say like the limit x goes to 0 of like whatever, right? That's another arrow, and this is a third arrow. We like arrows a lot in math because it's all about ideas moving around. But the point is, it's just a totally different arrow, so don't get confused there. So let's define a function that takes an input from 0 to 5, outputs things to real numbers, and specifically it's the function such that f of x equals 1 over x squared. It's a pretty nice function right there. Now, last time we talked about what it means for a function to be well-defined. We said functions must be well-defined to even be functions. And I guess the weird question is, if they're not well-defined, well, what are they? They're just things, I guess. We'll get to that in a second. But the point is, a function has to be well-defined. And I'll say, recall a function is well-defined if for each input we have exactly one output. And exactly one output, it kind of means two things, right? In a certain sense, exactly one means you can't be 0 and you can't be 2 or more. I guess that would be a weird way to think about it in real life. For example, if I say that I only have one nose, you don't go, well, why don't you just say you don't have 0 noses, you also don't have 2 or more noses? This makes no sense. It's just better say one nose. But in a certain sense, our functions actually makes us think about it this way. A function is well-defined if for each input we have exactly one output. And one output meaning not 0 and not 2 or more. And the reason we care about that is because it's kind of easier to prove it doesn't have 0 outputs and it doesn't have 2 or more than it is to prove it has exactly one. It's an interesting thing. But anyway, the point is that's what it means to be well-defined. Each input has exactly one output. And is that true here? Yes, it is true. We'll say note f is well-defined since for every x in our domain, the important part is for every x in our domain, 1 over x squared is defined and has one value. So that's why it's well defined, because 1 over x squared is defined, meaning it's not 0, and it has one value, meaning it's not more than 1. And this might seem obvious, but let's do some examples where this wouldn't be so obvious. If we had a different example, if we had a very similar function, f, that went from 0, 5, but including 0 this time, to r by f of x equals 1 over x squared, would this function be defined? Well defined. Well, let's start here. We just said that any x in 0, 5 is defined and has one value. So if it's not well defined, it must fail at the additional element we added, which was 0. And what's the problem with 0 being in the domain here?
Can't divide by 0.
Can't divide by 0. Note, f here is not, good job, Herman, well defined. I forgot to praise you correctly. Good job. This is not well defined since for 0, which we should note is in our domain, f of 0, which equals 1 over 0 squared, which equals 1 over 0, is not defined. So it's not true. So it's not true that for each input we have an output, because you plug in 0, there's literally is no output. This function is undefined, right? This is literally, we're getting down to like definitions, defined and undefined. Defined means it has a value. Undefined means it does not have a value. 1 over 0 just does not have a value. It's undefined. And we can think of wacky examples that we talked about last time where you can actually get more than one answer for each function if you do more than one answer for each function if you don't define it correctly. For example, what if we define a function g and we define g and we'll say this goes from the real numbers to the real numbers. No, I want this to go from the positive real numbers, including 0, to the real numbers by, I want g of x to equal the y such that y squared x equals y squared. Feels like a stupid thing to do, but this is a totally fine relation. Oh, I gave it away. This is a totally fine thing to talk about here. And that is, I want to plug in for any g, I want to output the y such that x equals y squared. But what's the problem with that? This is not well defined, not because it doesn't have, not because any element doesn't have an answer. Every element has an answer here, actually. For any g, for any x in the domain 0 to infinity, I'll say note, for any x in our domain 0 to infinity, the square root of x is such that x equals the square root of x squared. So y equals the square root of x is an output of g of x. So every single x in our domain has an output. The problem is it has more than one. However, we're going to run to the glare. We got to go below the glare. However, y equals negative square root of x is also such that x equals y squared. So negative square root of x is another output of g. Hence, there are elements in G. There are elements in our domain 0 infinity with more than one output. So G is not well defined. Oh, you can see that. And this is a weird situation here, but this is totally a function. This is totally a thing that would not be well defined. So G is not a function. You need to be well defined to be a function. Any questions? Good. And now notice that this definition kind of feels backwards here, But that's not the and I understand why you might feel that way if you've ever seen something like this before. But that's actually not the reason why this is not well defined. If we change this x to a y cubed, so we want g of x to output the y such that x equals y cubed for any x you plug in. And so, for example, g of 8, you go, look at 8 and you go, okay, what can I cube to get 8? Oh, that'd be 2. So that's how this function is defined. It would work like that. This function is well defined. Because anything in our input, anything in our domain has a single value output. Yeah. So anyway, the point is a function like this is a valid function. It's just the one with the square doesn't work because there's multiple things that square to the same value. Where cubes, there's not multiple things that cube to the same value, so we're good. Anyway, here's some functions. Let's talk about the range. So as we defined last time, the range of f is everything that gets hit by the function. So in this case, our function goes from 0 to 5 into R. The range of f is the set of all things that 1 over x squared hits if you plug in things in this interval to 1 over x squared. Another way to put that in set theory is this is all y in our codomain such that there exists x in our domain such that f of x equals y. And I'll say recall range is everything that gets hit by function. So that's this right here, It's all things in the codomain such that you can plug something in f in the domain and get that number. Everything that gets hit. So in this particular case, this would be all y in the real numbers such that there exists an x and 0, 5, such that f of x here is 1 over x squared. So you get 1 over x squared equals y. Now, let's talk about what this is going to be. I actually graphed this. Let's check out this graph here. Here we go. So if you look at this graph right here, here I've graphed f of x equals 1 over x squared on the domain we're talking about between 0 and 5, not including 0 and including 5. And so you notice if you look at this graph, the horizontal spot, right, the horizontal axis, that's x, that represents your inputs, and the vertical represents your outputs. And so for example, if you plug in 1 for x, right, you get 1 over 1 squared, which is 1 over 1, which is 1, so you get 1 for y. So that's a point on the graph. And if we look at this, right, if we plug in things closer and closer and closer and closer to 0, right, 1 divided by that square, you plug in numbers that get smaller and smaller and smaller and smaller. You do 1 divided by them squared, you get numbers that are bigger and bigger and bigger and bigger. That's exactly what's happening here. We're getting numbers that are getting bigger and bigger and bigger and bigger and bigger, approaching infinity. And if you plug in numbers as we get to 5, well, that's just gonna hit everything down until we get to whatever the heck 1 over 5 squared is, 1 over 25. So my claim is that the range of this function actually goes from 1 over 25 all the way out to infinity, or up to approaching infinity kind of thing. So everything bigger than 1 over 25. Let's prove it. Hope this makes sense. How do I stop doing this? Oh no. This should move. There we go. Stop share. Share screen. Here we go. So my claim is that the range of f, this right here, equals everything from 1/25 to infinity. That range right there, this interval right here. And so range of f is a set. This right here is a set, right? So to prove them equal, we need to do our set equality proof. It's exhausting, right? We need to do the set equality proof. And what that means is we have to prove that both of these things contain each other. And so the proof goes a little something like this. We'd say proof. Here we want to show range of f is a subset of 1/25 to infinity, and range of f contains 1/25 to infinity. That's what we're trying to show. So yeah, let's just get into it. So first you have to prove this side. And so this side, we're going to use the element method. So we want to show that for any element in the range, it's also going to be in this set right here. So we're going to say let x be any arbitrary / particular element of the range of f. Or y, actually. Let's do y, because we use y's for outputs. And ranges instead of outputs. Thus, by definition of range, if you're in the range, that means there exists some x, you can plug it into the function to get y. There exists an x in our domain, which is 0, 5, such that f of x equals y, which in this case means 1/x² equals y. Note, x in 0, 5, that means 0 is less than x, and x is less than or equal to 5. Thus, x² is less than or equal to 5², which implies that y, which equals 1/x², if we kind of flip both of these right here, that's going to equal, how do I get this back? There we go. That's going to equal, or that's going to be greater than or equal to 1/5², otherwise known as 1/25. So just manipulating this right here, we see that 1/x² is going to be greater than or equal to 1/25. What does 1/x² equal? It equals y. Hence, y is in 1/25 to infinity, because it's greater than or equal to 1/25. Thus, range of f is contained in 1/25 to infinity. Now, we need to go the other way too. So you prove this part, but you also need to prove the containment works in the direction, show these sets are actually equal. So let's go ahead and let y be in 1/25 to infinity. Thus, arbitrary but particular element in here. Thus, y is greater than or equal to 1/25. That's all it means, right? This said everything greater than or equal to 1/25. And if we know this is the case, so let's talk about what we're trying to show. So we have a y in this set. And remember, we're trying to prove this containment. We're trying to show that for everything in this set, you're in the range of f. And to be in the range of f, it needs to get hit by the function. So we want to show there must exist an x such that f of x equals y. We gotta go below the glare. Here we go. So let's think about this real quick. If we want x such that y equals 1/x², what's that mean? That means that we want x squared to equal 1 over y, right? Multiplying that and dividing by that. And that implies we want x to equal 1 over the square root of y. That would work, right? The real question is, will this x, which equals 1 over the square root of y, like notice if we take note 1 over x squared equals 1 over the square root of y squared, which equals 1 over y squared, which does, 1 over y, which does equal y. So plugging this into the function would work. The real question is, though, is this x in the domain? That's what we need to prove. And it turns out, since y is greater than or equal to 1 over 25, 1 over the square root of y is going to be greater than 0 and less than or equal to 5. So let's prove that right now. So what we got right now is f of x equals y. Oh, we wanted x such that f of x equals y. We know y is going to go to the square root. Y is greater than or equal to 1 over 25. Since y is greater than or equal to 1 over 25, the square root of y is greater than or equal to the square root of 1 over 25, which equals 1 over 5. Then that implies that 1 over the square root of y is less than or equal to 1 over 5, which equals 5. You have to flip we have to flip their equality, right? Because we're dividing, that's okay. Or I'm sorry, we flip the inequality because we're taking inverses, right? Like 3 is bigger than 2, but 1/3 is less than 2/3. Or sorry, 1/3 is less than 1/2. So it flips when you divide by 1. But anyway, we have this right here. So 1 over square root of y is equal to 5. Also note, since y is equal to 1 over 25, which is greater than 0, the square root of y is greater than 0. So 1 over the square root of y is greater than 0. Right, take any positive number, do 1 divided by that number, it's still greater than 0. So I'll say hence, let x equal to 1 over the square root of y. Note, x is going to be greater than 0, and x is going to be less than or equal to 5. So x is in 0, 5. Further, f of x is 1 over x squared, which is 1 over the square root of y squared, which is 1 over y, which is going to be y. Thus, there exists an x in 0, 5 such that f of x equals y, which implies, oh, you can see that, which implies that y is in the range of f. So we took a random y that happened to be in this set, but it came down and proved it must be in the range of f. There's gonna be some x that equals 1 over the square root of y in the domain that you can plug into f and get y. Hence, this shows that 1 over 25 to the infinity, hence this shows that the range of f contains 1 over 25 to infinity, because any element here must be in here. So since we proved the second term in both directions, therefore, range of f equals 1 over 25 to the infinity. Any questions? So at the end of the day, it's just a set equality proof. So proving that this set equals this set is just, if you're struggling with the set equality part, I mean, I don't say that's good, but at least it's not struggling with the range part. The important part is the range instead of everything that there is some x you can plug into f to get. All right. Now that we got that out of the way, So I got the problem with this function, or with this definition right here. This is the fun part. So the middle school definition says a function, the middle school definition, let's start on a good note. It says a function is a thing that takes in inputs from a domain and spits out outputs in a codomain, and we know it has to be well defined. Otherwise, it wouldn't spit out a single output. But the problem is, number one, what's the thing? Right? Well, exactly what kind of thing are we talking about here? And number two, the big problem is this kind of describes what a function does, but not describe like what it is, right? Like, I'm a math instructor. That's what I do for a living. But is that who I am? Like, kind of. But the point is, functions are more of a life than I do. And so functions, this is what they do, but mathematics, we like to look at them more as what they are, which is kind of a different and more interesting thing, I believe. So let's look at how we can do that. And the first thing we need to do that is define what a relation is. So this is going to be about relations. And I'll say, note, we oftentimes like to relate the elements of two different sets to compare / contrast / analyze / analogize, if we can make analogies, analogize, I don't know. The two sets. When I say we, I don't mean mathematicians, I mean freaking everybody. Like, for example, have you ever had a friend group, right? You're trying to figure out like, oh, how do we relate to the friend group and friends? Like, who's a Chandler, who's a Monica, who's a whatever? We guys should do that right now. So let's take our class as one set. So you have Daniel Valdo, that's me. You have Herman Rogers, you have Afra, you have Safa, you have Liam, and you have Patrick. And then we have the friends, Chandler, Monica, Joey, Rachel, Ross, and Phoebe, Lisa Kudrow. So how do we relate to the friends is the question. Who am I? Maybe you've never seen Friends, but I hope you understand the concept. These are characters of Friends. I'm going to say I'm a Chandler. I'm going to say Afra's Monica. I'm going to say Safa's Joey. I'm going to say Herman's Ross. I'm going to say Liam's Phoebe. And let's say Patrick is Ross. Don't take this to mean anything, anybody. I'm just making crap up. No, Phoebe's cool. Yeah, that's fine. So this is a relation, right, between us, the class right now, and the friends, right? I mean, people do this all the time. We like to make analogies between groups, like when you say that, you know. Well, actually, Friends is the best. They keep such a Chandler. I can't think of another thing that's not Friends, but you know what I mean. Right? Like when we watch TV shows, we like to oftentimes we see ourselves in the show. We relate to a character. We oftentimes map ourselves and our lives onto the show, where it's like, oh, their parents are like my parents and things like that. This is a relation between these two sets. These sets aren't the same. We can kind of find these strings that connect them, right? And so a relation a relation. What did I write? No. Between sets A and B is any way of relating the elements in A and B. That's just what a relation is. And so in our thing we have written down, the relation here, the blue relation, is we're relating me to Chandler. We're relating Herman to Ross. We're relating Afra to Monica. We're relating Patrick to Phoebe. On and on like that. This is the relation. Literally, relations are ordered pairs. We don't have to worry about that too much. The point is, we're just relating these elements. But you could have a different relation on these same elements, right? That's fine. These are the only ways you could do it, right? You could relate me to Rachel. You could relate Safa to Chandler. You could relate Herman to Phoebe. You could relate Liam to Joey. And then maybe you don't like the others. Maybe the other people, they don't really apply here, right? For example, if you're trying to map yourself on a TV show, trying to relate yourself to a TV show, and like the person in the TV show is an only child, but you have a sister or something like that, well, your sister just doesn't get mapped to anybody. They just don't exist in the show. Something like that, right? The point being, I'll say notice as we go. Notice a relation does not need to relate does not need to the relation does not need to relate some elements of A to any elements in B and vice versa. So sometimes in a relation, we'll have elements in the class that just don't relate, elements in A that just don't relate to elements in B, and vice versa. Like in the blue relation here, Rachel just didn't map to anybody. So Rachel didn't relate to anybody. There was no one here. And that's okay. It's still a relation. We're just finding things that do fit. We don't have to fit everything. Any questions so far? Good. Let's do another example. Let's say we have colors on one side and emotions on the other. So we'll have red, orange, green, blue, violet, and heck, I don't have a marker for it, but we'll have yellow, brown, gray, teal, something like that. And emotions will have angry, sad, happy, excited, nervous, frustrated. Are there any more other emotions? Bored, is that an emotion? I don't know. Let's stick with these. The point is, how do you guys relate these? I mean, red's probably angry. What do you see orange as? We're just making crap up here, people. No wrong answers. And Liam, don't tell me you haven't seen emotions. Maybe it means you don't see orange as anything. That's okay. How about green?
I see blue as sad.
I get that, Safa. Blue's sad. You're feeling blue. I see green as like excited. And I see violet as nervous. But I also see violet as sad. Yellow, I think of as a happy color.
Brown is definitely frustrated.
What do you say?
Brown should be frustrated.
Right? Teal. I don't know. Teal almost was like a no emotion, like Buddhist monk, totally chill situation. So I'm not gonna do blue teal either, unless someone has a better suggestion. Teal makes me sad. Okay. William doesn't like teal, so teal's also going to sad. We're learning a lot about each other today. The point is, this is a relation between colors and emotions, right here, right? And notice not every color is used in the relation. We used everything here, but maybe we didn't, right? Depending on who was making this thing, maybe nothing made them angry. Maybe red they also saw as more of a frustrated color, right? And so not every emotion used. That's fine. Maybe a bigger thing to point out is a violet and yellow, we both map to two things, or we both really related to two things. And sad, nervous, and frustrated all related to multiple things. So, big note, each element of A in a relation can relate to none, one, or multiple elements of B, and vice versa. So that's what a relation is. All right. So I'm already gonna tell you, by the way, the class is gonna go over probably about 10 minutes, maybe, because we didn't really have a third class this week. I guess we could have, but I didn't want to have a third class. We have the optional class tomorrow at 2:30. Just we're gonna talk about fun stuff, even funner than functions. But boys, just let you know, if you have to leave, don't worry about it. Leave whenever you want. All right. So that's what a relation is. So now our big definition oh, and by the way, that reminds me, we have one more thing that's a great common relation. We have the globe here, right? Sometimes called a map, right? And the interesting thing about a globe or a map is that everything on this relates to something on the actual Earth. So like right now, I'm pointing at Mexico. Here's where Mexico is. That on the map / globe, that relates to Mexico on the actual Earth. US is here, that relates to the US on the actual Earth. A lot friggin', what's this? Quebec is here. That relates to Quebec on the actual Earth. So a map is itself a relation between the Earth and this thing right here, which is kind of interesting, which is why we're going to use the word map for functions in a second. But anyway, because it literally gives us like a map to look at to take us from one place to another. But anyway, so a definition of a function. So a function is simply a relation a function from A to B is a relation between A and B that is well defined. So it's a relation between A and B that is well defined. And what's it mean to be well defined? This means every A in A relates to exactly one element of B. So just the exact same as the definition before. So the important thing is a function is kind of a one-way situation. So the idea of a function is we have these relations, right, where we have crisscrossing lines, all that kind of stuff, right? But a function really wants to be specifically ones where you can actually use it to go from one set to the next set. And so if it's like, so if we have, you know, if we go back to the class and the friends example or whatever, then you have DV, you have Chandler here, and I connected here or whatever. Like a function, you want to, if you had a function between the class and friends, that's something that you can plug any one of us into and you'll tell us which friend we are. It won't give us multiple options. It's not like, oh, Liam's a Phoebe or a Ross. No, it's Liam is a Phoebe or Liam is a Ross, right? A function wants to have one defined thing. And also there's no such thing in a function of not relating to anything. It needs to relate to everything. A function is we want to use a relation to be able to tell us, if you give me something in A, I will give you the thing it relates to in B, the one exact thing it relates to. So that's interesting. It's kind of a new thing. And it works one way, by the way. A function, every element A in our set A must relate to exactly one element of B, but does not say that every one element of B can't relate to multiple things in A, right? This function might send multiple different A's to the same B. That's fine. So I really like to think of a function. The way I like to think of it is I like to think of, so I have a set A here, like A1, A2, A3, A4. We'll have a set B here, like B1, B2, B3. I think of a function as literally like this laser gun, this laser beam machine here that, let's see here. That literally tells you where to like where that literally tells you, like, if you plug in any element of A into this F, it'll shoot it over to that B. It'll tell you that's where it goes. So A goes there. A2 goes to B1. A3 goes to B2. A4 goes to B3. I like to think of it that way because that's kind of literally what you're doing. You're plugging something in F, and it's taking you to where it is in B. Kind of interesting. Now, the important thing about functions is it has to be well defined. And here, notice this is well defined because every A here only goes to one thing in B. Now this B was hit by two things in A. A1 and A3 both go to B2. But that's okay because A3 and A1, they each go to one thing, B1, or like they don't go to multiple things or zero things. We know what the output of each of those is. So so it's fine. We have a word for this, a word for functions that a word for functions like this, where two things in the input map to the same thing in the output, that's called not being one-to-one. One-to-one functions are ones where this doesn't happen. So we can do some examples. Where's my example sheet? Here it is. So if we have like A here and B here, let's say we have 1, 2, 3, pi e in the square root of 2. And we go like this. So 1 goes to pi and it relates to e. And then 2 goes to this e and 3 goes to square root of 2. Is the function defined by this well defined? And notice what I mean by the function defined by this is I literally mean that f of 2 equals e, f of 3 equals the square root of 2, and f of 1 equals pi slash e. That's not divided by, that's like, goes to both. So is this well defined? We're getting a chat incoming. Patrick says no, and I believe Patrick says no is because of this right here. 1 maps to multiple things. So f is not well defined. And we say maps. Maps is like the verb of going through f. So when you go through f and hit element in B, that's mapping A to that thing in B. And it's called maps, just like I was talking about with the actual map, right? Because maps, in a certain sense, map the real world onto a very 2D nice little map. Like literally you could think of arrows from everything in the real world pointing to the thing on the map. Interesting. Anyway, yeah. What if so we can change this, right? We get a 1 here. And let's just say it doesn't go here. But now, actually, let's say it does go there. It doesn't go here. But now let's say this goes away. Is this well defined? I wish we had more time so we could talk about that. So we could really mull this over, but the answer is no, it's not well defined because 3 doesn't go anywhere, right? So not well defined. Since 3 does not map to anything. So the point is you have to be able to answer the question, what is f of 3? If you can't answer that question with one answer, it's not well defined. That's the whole point of a function. The whole point of a function is one relation that you can answer what is f of 1, what is f of 2, what is f of 3. You can answer what is f of whatever for whatever in your domain. Yeah, it made sense. Yeah. Okay, that's what we got going on here. Oh, and so just to give you an example of a function that is well defined, you know, if we had, it just really doesn't matter what we call these. If we have like this will be well defined because everything in A gets mapped to something. F of 1 is B, F of 2 is B, F of 3 is C. We just answered what is the function, map everything to with a single answer. We could even do this. It looks weird, but that's fine. That's still a perfectly valid function. Yeah. So now let's talk one-to-one and onto. Definition. A function f is one-to-one / we also call it being injective if no element in B is related to multiple elements in A. This function is going from A to B, by the way. So if no element in B is related to multiple elements in A. So real simple. If we have A here, we have B here, And we have 1, 2, 3, A, B, C. This function right here, not 1-to-1. It's not 1-to-1 because 1 maps to A and 2 maps to A. So this element here, this element A, is mapped to by 2 elements in our domain. So that's no good. And this is why we call it 1-to-1, because a 1-to-1 function is where one element in the domain goes to one element in the codomain. That's how they're related, right? And so that's kind of like, this kind of gets the idea of like what like a 1-to-1 correspondence is between things. Like if there was a 1-to-1 correspondence in our group between our group and the friends group, that would mean that each of us map to exactly one friend, and all the friends are mapped to. Yeah. But anyway, so this is what 1-to-1 means. Now, this situation right here, where we have like that, this is onto. Or sorry, this is 1-to-1. Since every element of B goes to exactly one element in A. Or sorry, every element of B goes to one or fewer elements in A. Because if we had a D here, this is still onto. Because B is related to just B can't be related to multiple elements in A, but 5 is related to 1 or less. Any questions? Let's do an example real quick. Example. Let's do f from r to 0. So f to the positive or greater than or equal to 0 real numbers by f of x equals x to the 4th. Claim oh sorry, I want x cubed. Claim f is 1-to-1. So here's how you prove something's 1-to-1. We prove a function is 1-to-1 by setting 2 outputs, f of A and f of B equal, and proving then that A must equal B. So the way you prove two functions the way you prove a function is 1-to-1 is it's kind of a contradiction-like thing, but not really. You're kind of going like, okay, let's assume there are elements A and B such that f of A does equal f of B. And then you're proving that A must equal B, which basically means that, well, if f of A equaled f of B, then we must have A equals B. So it can't be different. There can't be 2 different elements that map to the same thing in B. Therefore, F is 1-to-1. So assume there exists A and B in R. This should be R to R, I'm sorry. A and B in R such that f of A equals f of B. So A of B and R, we use R here because it's the domain. So assuming there's just an A and B in the domain, so the f of A equals f of B. Thus, this means that A cubed must equal B cubed by substitution. Because that's what f equals. That's what f of A, f of B equal. Hence, a cubed minus b cubed must equal 0. Zero by subtraction. And that implies, if you guys remember factoring rules, that a minus b times a squared plus ab plus b squared equals 0. All right? So thus, by factoring, thus a minus b equals 0, or a squared plus ab plus b squared equals 0. All right. Now, I don't want to waste your time. I'll say we can prove that a squared plus ab plus b squared cannot equal 0. If we had time, we'd do it, but we don't have time. So we can't prove that a squared and a squared cannot equal 0. So thus a minus b must equal 0, which implies a equals b. Therefore, f must be 1-to-1. The point is, we started here assuming this, and we ended with this. So you start by assuming they have two things that go to the same element in B and prove they must be the same thing in the domain. So this proves that there can't be two things in the domain that map to the same element in B, same element in the codomain, because if they do map to the same thing, they must be the same thing. They must be equal. So they can't be two different elements, I should say. Any questions on this? All right. Now let's talk one on two. We say a function is onto / surjective is what we call this. A function, I'll say a function f from A to B, if every element in B is in the range of f. So we're saying that every element of B gets hit, i.e., for all y in B, there exists an x in A such that f of x equals y. So to prove a function's onto, we need to prove this right here. All right, and so to do that, let's say, let's do a, and this, by the way, is standard proof. It's a universal statement with an existential statement, so we have mixed quantifiers here, but we know how to do this kind of proof. Let's do an example of f from 0 to infinity going into the real numbers by fx equals ln of x. Claim. F is onto. So notice a big thing here with functions. I was saying that our middle school definition looked at functions as things that did something. They only looked at the function of a function, but we like to look at functions as actual things themselves that have properties. That's why we say f here. Notice there is no f. We're not saying f of x. We're looking at f outside of its context to x. Right? We're looking at f outside of its context to any input. We're saying the function f itself, it's a thing that's onto. Interesting. Anyway, though, it's like when you start seeing your parents as independent people themselves. The point is f is onto. How do we prove this? So proof. So we're just going to straight up prove this right here. So we want to show that for all y in the codomain R, there exists an x in the domain 0, infinity, such that f, which is just ln of x equals y. Okay. How much time do we have? Here's what I'm gonna do. This can be done. We don't have time today. I think I'm going to make some optional videos where I go over some of this stuff so you guys can watch it if you want, if it helps you with your exam or whatever, if it helps you study. I'm not gonna put it right now because we have another definition to get into. But the point is, for things like this, that you can do it. I mean, maybe a real easy one would be like, let's say we had f of x equal to, let's say 2 times x. Well, f is onto proof. So I'll prove for all y and b. I want to show for all y in R, there exists an x in 0, infinity, such that y equals 2x. So let's let y be any arbitrary / particular element of the codomain R. This should be R to R now. Note y over 2 is in R. Let x equals y over 2. Then f of x, which equals 2 times x, will be 2 times y over 2, which equals y. Thus, there exists an x such that f of x equals y. Hence, for all y in R, there exists an x such that f of x equals y. Therefore, f is onto. That's the structure. Okay. One last thing, and then we'll get out of here. I will go through and comb through your quizzes to get rid of stuff that we didn't go over properly, because we're at the end of the year. This is just stuff we're trying to get to anyway. So definition of bijection. A function f is a bijection bijection from A to B if f is 1 to 1 and onto. So a function is a bijection if and only if it's one-to-one and onto. Why does that matter? Well, it matters because if you think about it, if you have like A here and B here, 1, 2, 3, A, B, C, whatever it is, if the function is one-to-one, that means that no two things in A go to the same thing in B. So we can't have that or anything like that. They're all going to go to their separate things. And if a function is onto, that means everything is hit. But here's the thing to think about. I wish we had like a whole class for this. If we can draw a line between everything in A to everything in B, right? We can draw a line like this, where everything in B is hit, and no two things in A go to the same element. What's that mean about the size of these two sets? It means they're the same. I mean, think about it, right? Like, I have 1, 2, 3 markers here. And I have 1, 2, 3 pins here. How do I know I have the same number of markers as pins? I know because I can match them up. I can relate them like this. I can pair them off and go, okay, there must be the same number because each marker relates to a pin. There's no pins left over. That's exactly what's happening here. In a certain sense, what 3 means, the definition of 3 is just the term we give to the size of all things that we can pair up to these markers right here. If you compare them up to these markers right here, we call it having a quantity of 3. It's weird to think about. The point is, if two sets, if there is bijection between two sets, their cardinality, which is a fancy word for their size, must be the same. So, last definition. Sets A and B are said to have the same cardinality if there is a bijection from A to B. Because if there's a bijection from A to B, that means we can pair up the elements in A and B. If you can pair up the elements in A and B, well, of course, they must have the exact same size. That's the idea. And so I will say note, one example, and then we'll leave. Example, Z and 2Z, which remember are just the evens. Elements that form 2n such that n is in Z, have the same cardinality by f from Z to 2Z such that f of n equals 2n. We can show that this is a bijection, and we can show this is a bijection from Z to 2Z. meaning we can actually pair up the elements of z and the elements of 2z. We can pair up every integer with every even number. And so in a certain sense, there are the same amount of even numbers as there are integers. It feels weird. It feels like there should be less, right? Because like every other integer is odd, right? So there should be less even numbers than integers. But in another sense, not really, because if you look at a number line, we have 0, 1, 2, 3, 4, -1, -2, -3, -4. If you look at the evens, so the integers are all the blues, and the evens are all the reds. And if you think about it, because these go on infinitely in both directions, if you stretch out the number line, stretch out the blues by double, you'll hit the reds. So it's not that there's less even numbers than integers. The evens are just more spread out. They have a lower density, but because we have an infinite number line here, that's okay. And we do this for a lot of things. And so I'll say common notes, common facts, Z and N have the same cardinality. Z and Q have the same cardinality. And then we have 0, 1 and R have the same cardinality. And we have that R and N have different cardinalities. And anything in here anything with finite cardinality. So if you're just like the set 1, 2, 3, you're just like your 3. Anything with finite cardinality or cardinality same as N is called countable. Anything with cardinality greater is called uncountable. And then we're done. There's a bunch of facts that I need to spew out at you. It would be insulting if you guys didn't see these in the discrete math class. We went a little slow this year, so we had to kind of pack in towards the end. So sorry about that, people. But anyway, the class is over. The class is done. We're done. So yeah, does anybody have any questions? All of this stuff we covered at the end, we're gonna just briefly touch in the exam, more in a factual way, not in a way you're gonna have to actually like do anything too extreme because we didn't get the chance to do much with it, sadly. But yeah, any questions? Okay, well, Liam, we have business, right? Oh,
Bye, Professor.
yes, Safa. Sorry for going over. It's been a pleasure teaching you this semester. Maybe I'll see you tomorrow in the fun lecture or in an office hours, but if not, stay cool.
You two take care, Professor.
Thank you, Safa. Stop recording.